higher speed on top, lower speed on the bottom, we'll have a pressure difference. Higher pressure on the bottom than on the top. And that pressure will push up. And that pressure could support this thing. Okay? So we're very much now aerodynamics. Air has to be moving. If we've got no velocity here, we've got no pressure difference. Right? No hydrostatic. So there's Bernoulli's insight into this. But that really doesn't say how we get that pressure difference. Or the velocity difference, rather. So we know how to get the pressure difference. To get this to be a non-zero number, we have to make this different. That has to be non-zero, but how do we make that happen? That's the next step. Okay, so the next thing we'll look at, let's look at air or water, any fluid moving through a tube. So here we've got a tube. We'll say this is a circular tube. Okay, looking at it from the front, it's just a circular cross-section. It doesn't have to be that way, but we'll simplify it by saying that. So we've got this tube, and this tube has a certain area. We'll say the area is A. We're talking about area like this, if you looked at the cross-section of it. Okay? And we're going to have air moving through this thing at a certain speed. So there's a velocity that the air has as it moves through that tube. So we've got a certain area-sized tube, like a big pipe or a duct, and we've got air moving through it with a given velocity. If we were to take the velocity with which the air, water, whatever, is moving through this, times the area of the pipe through which it's moving, then let's see what we get. Velocity times area. What are the units for velocity in basic English units? Feet per second. Here we go. So we have feet per second. And then if we multiply that times area, what are the basic units for area in the basic English system? There you go. Square feet. If you multiply feet per second times feet squared, what do you get? Feet cubed per second. So cubic feet per second. Well, what is cubic feet a measurement of? Volume over time. This is what we call a volumetric flow rate. Volumetric flow rate. We symbolize that with capital letter Q. So if we take the area through which something flows times the speed with which those molecules are moving, we get a volume flow. What are some other units for volume flow that you might be familiar with? If you're a pilot, you talk about volume flow with your fuel in what units? Gallons per hour, right? That's a volume over a certain amount of time. That's the volume of fuel that's being pumped through that engine in an hour. 10 gallons per hour. That's a volume flow. So we talk about this. In plumbing, you talk about this. In HVAC, you talk about this. Whenever you've got a fluid moving through a duct, you've got a volume flow. So velocity times area gives us a volume flow. So in this case, we've got a certain volume flow of a fluid, could be water, could be air, doesn't really matter, moving into this pipe. Now think about this for a minute. If you've got a certain volume flow coming in, we could talk gallons per hour, we could talk cubic feet per second, doesn't really matter the units. If you've got a certain volume flow of fluid coming into this, what do you think you'll have coming out? Should be the same, right? Let's talk about water. If you've got 1 gallon per minute coming into a pipe, coming out of the pipe should be 1 gallon per minute. What is that based upon? What conservation principle do you think that's based upon? Mass. If you've got mass being made up somewhere, you'll have more coming out than came in. If you got mass disappearing somewhere, you'll have less coming out than you had coming in. So most basically, this is conservation of mass. Whatever goes in has to come out, or at least be accounted for somewhere. So if we know that we got a velocity coming in, and we've got an area coming in, and we'll call the in condition 1, that means we have a volume flow right there in condition 1 coming in. If the exit is condition 2 of this pipe, what you've just told me is that the volume flow in condition 2 is the same, right? The volume flow coming in and the volume flow leaving are the same. Now intuitively we kind of feel that. 1 gallon per minute coming in a pipe, you know there's got to be 1 gallon per minute going out because no water's disappearing, no water's being made up. Okay? What goes in has to go out. So that's pretty intuitive. When we say this, remember, whenever we've equated something in two conditions, what's a more basic way to state that? Volume flow is what? Constant. When we say that, and this is the same thing, but let's state that. When volume flow is said to be a constant, this is what we call the continuity equation. Continuity. It means that volume flow is continuous. It doesn't change. It's a statement of conservation of mass. So there's another principle. We feel that one. We know that one. That one's pretty intuitive. Now there is a more basic version of this one, but we'll stick with this for right now. Let's finish this out. Let's expand it back to what we saw here. If it's constant, then volume flow in one condition has to equal volume flow in any other condition. So that's expanded out from what we've done before. Kind of like saying this is constant. We can look at it in two conditions. It has to be equal. So you can do that when anything is constant. But we can also spell this out further. We know that volume flow is equal to the product of velocity and area. So in condition 1, we've got velocity in condition 1 times area in condition 1. That's the volume flow in condition 1. And then somewhere else in the pipe, we look at the volume flow in some other condition. Here we've got condition 2 over here, the outlet. Well, that's equal to velocity there times area there. So there's a little bit more filled in version of the continuity equation, one we can actually work with. If we look at the pipe that we have right here, what does the area of the pipe here look like compared to here? About the same, right? If this area is the same as that area, what can you say about this velocity? It's going to be the same, right? Because those two products have to be equal. But here's where the interesting part comes in. If we modify this pipe, so in your dry erase notebooks, you can make this modification. If you take your pipe and you make a change like that, we narrow the pipe. We neck it down or throttle it down. What is the area here? Smaller. So we've got a different area. We can't say it's the same. So we've got an area that's different. If this area goes down, according to this, what does this velocity have to do? Go up. So if that goes down, that goes up. That's according to continuity. So we'll show this velocity, V2. It's got to be bigger. It's got to go up. Now we all feel this one too. We've experienced this. And if you haven't, maybe I'll talk you through a mental exercise. Who in here has ever used a water hose? Anybody have some experience with that, been signed off on a hose usage? So if you take a water hose, you know, the area of the opening is about yay big, and the water comes out with a certain velocity, just kind of dumps out, no attachments on it. If you take right or left thumbkin, doesn't really matter. If you take right thumbkin and put he or she over the end of that hose, what happens to the area of that hole? It goes down. What happens to the velocity of the water coming out of that hole? It goes way up according to continuity. So how do we affect a velocity change for a fluid? We change its area. We change the area through which it has to flow. And this is the change. If area goes down, velocity goes up. Or if area goes up, if we made this pipe bigger, the velocity would go down. So the same volume flow can keep passing through it. And the same number of molecules, hence volume, has to go through that pipe, whether the hole is big or small. If the hole is small, they have to go faster to get through. If the hole is big, they can go slower to get through. Now here's where this ties back into this. If we change the area through which a fluid flows, if we make the area go down, the velocity goes up. That's continuity. But if we take that to Bernoulli, if velocity goes up, then that causes pressure to go down. So there's the tie-in. An area change gives us a velocity change. A velocity change leads to a pressure change. Okay? And a pressure change we can do something like that with. Okay, so two basic principles you have to know to get there. Bernoulli's and what he says, or what that law says, pressure and velocity connection, and continuity and what that says, the velocity and area connection. So typically, where this shows up in a tube like this, it goes with a name. Some of you who've been in aviation know this, Venturi. There was an Italian scientist named Giovanni Venturi, and he studied this. He studied flow in channels. Here's another example of how this works. If you look at water flowing through a channel, flowing through a river, if the banks of the river come closer together so the channel narrows, or if the bottom of the river gets closer to the top, it gets shallow, what does the water speed do? It picks up, and he studied that. Okay, so he came up with, or he worked with this, and so we name a device after him that looks sort of like this. It's a tube that has an area reduction in the center. That's called a Venturi tube. We used to use these a lot in aviation. In a Venturi tube, you got an area of the opening, we'll call this A1, and you've got an area where there's a reduction called the throat. So this is A2. You've got air coming into this. So these things used to be strapped to the outside of airplanes. It'd physically be on the outside on the fuselage. And so there's air coming into this thing, V1, velocity 1, based upon your flight speed. So whatever your true airspeed is, that's the airspeed coming into this area. But then when the area goes down, the velocity does what here in the throat? It goes up. So you've got a higher velocity through the middle, V2. But that's not all we did with the Venturi tube. So this is the velocity that enters that area, but the atmosphere coming in has a certain pressure, so we call that P1. There's a certain atmospheric static pressure of the air coming in. So when the air enters with this pressure at that velocity, it goes through this lower area that increases the velocity, but it does what to pressure? Lowers the pressure. So you get a different pressure here. We'd have to call that P2. And we could write this in a simple form. So we could say if A2 is less than A1, here's a simple relationship so you can follow this through, then velocity 2 will be greater than velocity 1. Put commas at the end here. Then pressure 2 will be less than pressure 1. So those are all the things going from the continuity equation to Bernoulli's equation. So the area change affects the pressure change. You can see these are always inverses. If area 2 is less than area 1, velocity 2 will be greater than. If velocity 2 is greater than, pressure 2 will be less than. So they're always the inverse of what happens if it helps you track it through. But if you know the equations, this one and that one, you can follow that as well. So now what we've got with the Venturi tube is we've got atmospheric pressure and we've got a lower pressure in the throat. So basically like a weather system, we've got a high pressure system and we have a low pressure system. From high to low in weather, what do you know? From high to low, the wind will blow. That high pressure always wants to equalize and blow to the low pressure. So here's what we do with that. The air's already moving through there, so that's not a big deal, but we also can connect this and make a little circuit. So we can make basically a parallel circuit through this. And in this little circuit, we can insert what is like a windmill. So we've got a little, I'm going to draw it like a paddle wheel because that's easy to draw, like a paddle wheel in a river at a mill. So we've got a little paddle wheel there, we call it a turbine. If this is a higher pressure here and a lower pressure here, from high to low the wind will blow, and one way that wind can blow is through that little circuit. And so when that air blows over this turbine, it forces it to spin, just like water forcing a wheel in the river. So when that thing spins, now you can drive something with it. And the something that we drove with those were gyroscopes that drive attitude indicators so we can tell what our orientation is. So we use this pressure difference given to us by this area difference to get velocity moving through that tube to drive a turbine to spin a gyro. That's what Venturi tubes were used for. Anybody else have any other idea where a Venturi tube might show up on an airplane today? Carburetor. So a carb is a Venturi, right? You move that throttle, it closes down that gap, it restricts it, so the speed has to go up, and when the speed goes up, pressure goes down, and it draws more fuel in because there's a low pressure system, okay, compared to what the pressure outside. There's another hand up. Anybody have anything else to add or ask? Okay. So there's the tie-in. That's what we use with a Venturi, but we still haven't got